Good afternoon, everybody, and welcome to our Pi Day of Giving virtual speaker series event, Pi in the Sky, with Dr. Rupinder Brar. As a university community, we are dedicated to increasing our awareness, understanding, and gratitude for the lands we share. So before we kick off today's presentation, I'd like to acknowledge the lands in which we're gathering on today. Our university campus is situated on the traditional territory of the Mississaugas, a branch of the Greater Anishinaabe Nation, which includes Algonquin, Ojibwe, Odawa, and Potawatomi. Because everyone is turning in with us remotely across a variety of cities, we really don't want to forgo this important element of reconciliation. So I'd ask that everyone take a moment to reflect on the traditional territory that you're on, the treaty that it's covered under, and your own personal relationship with the land. My name is Jody Cowan, and I'm the Community Engagement Coordinator here at Ontario Tech. Today's session with Dr. Rupinder Brar is the 9th of 10 amazing sessions we're hosting with our Ontario Tech experts to share their research with us and spread the word about our Pi Day of Giving. This will help raise funds for our Student Relief Fund, which helps students who are experiencing a financial need due to COVID-19. I would like to take a moment to thank those of you who made a gift upon registering for today's session. There will be time for Q&A following Rupinder's talk, so I encourage you to use the Q&A function at the bottom of your screen at any point during the presentation, and we will do our best to get to them all. These sessions are being recorded, and you can watch them again later on our Pi Day of Giving website, or you can share them with your friends who weren't able to make it with us live today. I would now like to introduce our speaker for today, Dr. Rupinder Brar, who teaches physics and astronomy to students in all disciplines and levels here at Ontario Tech. Welcome, Rupinder. As an Associate Dean Undergraduate Studies, he is focused on enriching the learning experience for students throughout the faculty. Dr. Brar has won numerous awards for his teaching, including the title of Ontario's Best Lecturer and TVO's Big Ideas Best Lecturer competition. He enjoys taking an active role in science outreach and public education. Rupinder gives public lectures to a wide variety of groups locally and abroad and appears in various media as a physics and astronomy educator and expert. So now I'd like to turn it over to Dr. Brar for his presentation, Pi in the Sky. So please take it away, Rupinder.
Everyone, very, very much my pleasure to be here. Just gonna get my talk up. And thank you so much, Jody. It is called Pi in the Sky, and I just want to make sure that everyone can see it and see me. We're all good to go? All right, great. So again, welcome. We're going to jump right into things just because my time is limited, but I do want to thank you all for coming out today. And basically, I want to start today with a little question. I want you to think back to grade school when you were studying space for the first time, the solar system. We all had these projects in grade 3 and grade 4, and oftentimes we built our own solar system. Do you recall how many planets there were when you were a kid? How many planets did we know about back then? I feel like a good number of people are probably saying 9 right now. A few, maybe even 8, if you're very, very young and joining us today. Pluto was demoted as a planet at some point from probably when you were a kid to now. And so we knew about 8 different planets. But since then, we've learned about many, many more planets, not around our own sun, but around other stars within the Milky Way galaxy. But this is a relatively new discovery. In fact, it was in 1995 that we discovered our very first planet around another star. And that planet is called 51 Pegasi b. It's not the best name in the world. It's not as cool as some of the planets in our own solar system, but it is going to make very logical sense as to why that is the name. I will mention that just recently in 2019, this discovery was awarded the Nobel Prize because what it did was it started a revolution of understanding worlds in other systems. And to today, I checked this number just this morning, we have now discovered 4,687 planets around other stars outside of our own solar system. Other than the 8 in our own solar system, we know about 4,687. Those have been confirmed to exist. Now, those planets, they live in 3,463 solar systems, and about 770 of those solar systems, actually, we've found multiple planets in them. So my question to you is, does that seem like a lot? Have we now discovered a lot of planets? I would say no. I would say no, because when you think about the number of stars that we know about, the number of galaxies we know about, they far, far exceed this number. We're talking more like many orders of magnitude bigger than this. And so I ask you, why is the number of planets we know about so much smaller than the number of stars and the number of galaxies? Well, you probably guessed it's because it's hard to detect planets. It's very, very hard to detect planets because they're relatively small and relatively dim in comparison to the other stuff that we're talking about. And so trying to find a rocky world or even a gas giant like Jupiter near a parent star. So we think of this little planet here as a planet, and let's just say we have a big star around it. Let's say this light right here represents our planet. The star is so bright, the star is so big, to see a little planet near it is very, very challenging. A sun-like star is probably 1 billion times brighter than the planets around it. And so to see those planets from the stars is very difficult. I give the analogy sometimes, it's as if, imagine shrinking our star down to the size of a grapefruit. Well, the next nearest grapefruit, that is from star location to star location, would be the equivalent of the distance from Toronto to Vancouver. So once again, we've got our own sun. We shrink it down to the size of a grapefruit. I put it down in Toronto. The next closest star, the next closest grapefruit is in Vancouver. Oh, but we're not looking for that that grapefruit. We're actually looking for a tiny, tiny object near it, about the size of the tip of this pen. If you can see the tip of that pen right there, that would be the size of Earth on this scale. And so now we have to look for that tiny tip of a pen in Vancouver. And oh, by the way, it's right beside something that is 1 billion times brighter than it. And then what that does is it creates a very big challenge for astronomers. We realize that when we want to find planets, most of what we're going to actually be looking at isn't looking for the planet itself, but looking for the effects of the planet on its parent star. If I can't see this planet, if the planet is so challenging to see, what I'm going to do is instead, I'm going to look at the star itself to see if it demonstrates any qualities or changes or properties because there's a planet around it. And so if you want to find planets, there's two ways to do it. You can do it directly or you can do it indirectly. If you're looking to directly take a picture of a planet, it's super challenging. We have done it ever for 51 planets now. 51 of those 4,000 whatever have actually had their photographs taken. We'll talk more about that later. But the remainder of the discoveries, the 4,300 plus of them, have actually been found by indirect measurements. And indirect measurements means looking at the star itself and seeing if it gives away the presence of the planet. And so I ask you this to think about. What effect does a planet have on its star? If I'm looking at a star very, very far away, this pinprick of light, what effect can I see of the planet on the star? I'll give you a second to think about that. The first effect is going to be a gravitational tug. So when we have two objects going around each other, I've got these two rocks in my hand right here. If they were orbiting in space and they were about the same mass, they would actually be orbiting like this. I'm gonna make sure I'm on camera here. They'd be orbiting like this, around some center of mass, When we look at a planet going around a sun, such as the Earth going around our sun, it doesn't look like the sun itself is actually moving, that it's just kind of sitting there in the middle and the Earth is going around. That is not the case. They both orbit some center of mass between them. Because stars are so much more massive than planets, that center is closer to the center of the sun itself. So what the sun does is it doesn't orbit, it wobbles. And so, for example, if you think of my head as the star and there was a planet going around it like so, I would just get this wobbling motion like this. Does everyone see that? And so the question is, can we detect that wobble? Can we look at a star in a far off distant star system and see its wobble because of the planets around it? Well, let's take a look first at our own solar system. And that squiggly spirograph pattern that you see there, that spirograph pattern is the motion of the center of our sun because of all the planets in it. So we could look at that motion very carefully. And you see that line all the way from 1960 to 2025. Oh, it's predicting the future. We could see the motion of the sun due to all the planets, and physicists can actually take that information and translate it and learn about the planets. They can figure out how many planets there are. They can figure out the masses of the planets and all of this cool information about the planets itself without ever having seen it. There's only one problem. There's only one problem. These little wobbles that we're talking about, they're tiny. They're tiny. And though we can see our own sun wobbling, we can't actually see the wobbles in other star systems. So why am I even teaching you this technique? Because we don't measure the motions of the stars. We measure their velocity or speed. And it turns out that detecting or measuring the motion of a star in space is very hard. It's hard to look at something that's light years and light years away. Again, think about a grapefruit sitting in Vancouver, just kind of going like this. Can we tell it's even moving from Toronto? It would be hard. But what we can do very, very accurately is measure its speed. We have a technique called the Doppler technique. I don't have time to get into it, but with the Doppler technique, you can actually measure the velocity of an object to as small a value as 1 meter per second. 1 meter per second. That's just like walking speed, right? Just like, well, average walking speed. And so if a star is doing this wobble, we can tell from its speed. Okay, great. We now have the ability to detect the wobble. So the question is, what do we find? Well, if you look at the star 51 Pegasi, that's the name of the star where we found our first planet, then we do see that wobble. And that's what this picture here represents. That wave there, that shows us that the velocity or the speed is changing as it goes towards us, away from us, towards us, away from us. That wobble is detected by the change in speed. And we can learn about that planet. We can figure out, for example, how long its orbit is. Turns out the planet's orbit around the sun is 4 days. Whew, that's really short. We also can detect its mass. Turns out its mass is as massive as Jupiter. Well, that's very strange. So suddenly we're finding a Jupiter-like planet who has an orbit of 4 days, Earth days, that is. That's much, much smaller than we would expect. Very strange planets out there, and we'll find them stranger still. The next technique that I want to talk about, which is the one that we found the most planets with now, is called the transit technique. And this is what happens when a star has a planet going in front of it. So once again, we've got our star here. So you can see the light shining towards you. We're sitting here on Earth and we're looking at these stars. We're looking at all of this starlight coming towards us. We can't actually make out the size of the star itself. These stars are so far away that it literally looks like there's a point of light coming towards us. But if we keep watching that point of light and suddenly something goes in front of that light and blocks it, like an eclipse, like also known as a transit, if it's much, much smaller, usually it'll be quite a bit smaller, and it goes in front of it and it decreases the amount of light. We can learn about the existence of planets by just looking at these stars and waiting until a planet goes in front of it. When a planet goes in front of it, if it has the right shape, the light dips down, goes to some minimum, then comes back up. That indicates the presence of a planet. And the amount of dip can actually give us the size of the planet itself. We can start to learn so much about these worlds without ever having seen them. These techniques are getting better. What we're learning about the planets is getting more and more advanced. And we are actually getting better at taking photographs of planets as well. And so you can see right down there. Yeah, there it is right there. The first photograph we've ever taken of a planet, what we use is some special techniques. We're actually able to eliminate the very bright star at the center to look at the planets. And what you're looking at right over here is the planet Fomalhaut b. Fomalhaut b is just called that because it is the planet around the star Fomalhaut in the year 2004 and 2006. So you can see that that planet has moved in 2 years. It's very difficult to do, but we have been getting better and better at it. Here's a photograph of a system where in this system, we actually have detected 4 planets. There's 1, 2, 3, and 4. We've taken this picture over years and years too, and you can find videos of those objects orbiting their sun. This little bit right here, that's just the sun that is covered up, where we're trying to block the light from it. And so our first imaging of planets only happened in 2008, and up to now, we've done it about 51 planets for 51 planets. All right, so what can we learn about these planets as our technology is getting better and better? We can learn the orbital period of them. We can learn the distance from their home stars. We can learn the shapes of their orbits, the mass of the planets, the size of the planets, the density of the planets, and in very, very rare occasions, but we're going to get better and better at this, the atmospheric properties of the planets as well. We're learning about all of these things for these distant worlds. And so I guess the question then is, how are we doing it and what are we finding? Looking at the time, I'm going to skip over this bit really quick. We've been doing this with a number of different with different satellites, including Kepler, Gaia, and TESS. And what we found out is that there's plenty of planets out there, and some of them have very much Earth-like features. And we want to ask ourselves, what happens when we find an Earth-like planet? What happens when we find a planet that has a similar gravity, temperature, atmospheric composition, and maybe number one of all, liquid water on its surface? Not necessarily life, but the conditions as we know it that are suitable for life. Well, no, we don't have to ask that question because we found it. We found it here on Kepler 186f. This is, of course, an artist's representation of this planet discovered back in 2014, and it has a very similar characteristics to our Earth. It is considered the first habitable planet outside of our own solar system, where it has a size similar to the Earth and a location in its sun's orbit such that we can, in fact, see have liquid water on it. And so this was just the first of what will be many stars. The Kepler telescope was able to do a statistical estimation of the number of planets that could be considered habitable by the loosest of sense, like having similar properties to the Earth. And the number is somewhere between 11 billion and 40 billion planets within our own Milky Way galaxy that we could be considered Earth-like. And so it's interesting, right? Because growing up, again, we've always been told reduce, reuse, recycle, take care of your planet. There is only one planet. Turns out there are other Earths out there. Now, of course, we have to take care of our own Earth because going to these planets is going to be, and we need to take care of the one world that we are able to reach that can actually support life. But it's just so fascinating that these worlds are out there. Remember when I talked about that grapefruit in Vancouver? Turns out that it also has a planet around it. It itself has a planet that is just 1.3 times Earth's mass. So even the very closest star to us, we know has an Earth-like planet. I mean, there's some things that will probably make it uninhabitable, but it's just fascinating that we're just on the precipice of this whole amount of information and discovery about what these planets are like. It's just incredible. Another very interesting solar system, which I think people really enjoy, is what's called the Trappist1 system. Here we've actually got 7 rocky worlds in it. We can compare them to the rocky worlds of our own solar system, and you can see that they're relatively about the same size as the Earth. Most of them are close enough to their parent star that they would have liquid water on them as well. The last planet that I want to talk about is the Pi planet. Since this is Ontario Tech's Pi Day event, there is a planet called the Pi planet. And it has been given that name because its orbital period is 3.14 Earth days, 3.14 Earth days. Now, does that mean anything? Is there any significant? No. It's just a really, really fun, big coincidence like astronomers like to grab on. But this particular planet is also not so dissimilar from Earth. It's about 81% of the mass of the Earth. Its average temperature is way, way, way hotter than the Earth. But it's only 185 light years away. And so the last thing that I want to leave you with is we are now at the point in this field where we are discovering Earth-like planets all the time. The question is, how close are we to discovering not just habitable worlds, but worlds that have life on them if they do? Our technology is getting better and better and better, such that we're getting to the point where we have the ability to tell the atmospheric composition of some of these worlds. Well, when you look at the atmospheric composition of Venus, Earth, and Mars, there's a big difference between them. We have an oxygen and ozone in our atmosphere because of life, because of respiration of plants. The technology is such that we will soon be able to detect these sorts of signals from faraway worlds. And I'm not saying they're out there, but I'm saying if they're out there, if life is common on these worlds, and if it exists in a form that is familiar to us, is similar to ours, we're very, very close to the edge of being able to tell that it is in fact out there. So for me, this is the most exciting field of astronomy. And looking at the time, I think I better wrap things up and take your questions. Thanks very much, everyone.
Thank you, Rupinder. I can definitely see how that Ontario Tech Expert Award was given to you. It's the one by TVO. This has been fantastic. So thanks so much for sharing your expertise with us today. A lot of questions coming in and a lot of comments from our participants today about your setup. And we're wondering, is how you're presenting to our students during their virtual learning?
No, it's even better for the students. So that with the students, what I do is I use a mix of asynchronous and synchronous learning. And so synchronous is similar to this, but my asynchronous stuff where I'm giving them a lot of content before they come to class. I like to kind of flip the classroom a little bit where they get a lot of the content. Those lectures are even, let's say, of even higher production quality. And so I do film those. And I edit them in front of my green screen, and it's even more immersive still. I'm able to do a little more special effects because I do editing afterwards, while here, because it's live, it's a little bit harder to do. So this is just this is the minimum. I go even farther than that.
Well, our students are extremely lucky to have you, so thank you for that. Questions about the planets. Planets like the Kepler planet that are similar to Earth. Number one, how close are they to us? And will they ever be renamed? Because like you said,
yeah,
most amazing name, right?
So I hope the renaming happens because some of them are really, really important. And it would be nice to give them something a little more fancy. So usually the naming convention currently is you take the name of the star and then you add the letter B to it for the first planet discovered, C for the second, D, E, F, like that's it. That's the entire thing. The telescopes that have been discovering these worlds, they've started to name the telescopes after them, which I think is even more boring, to be honest. So it's like Kepler 186F, yeah. So I hope so. I hope so. The International Astronomical Union is in charge of the official naming convention. What was the first part of that question? Oh, how far away? A lot of these planets, in average, I would say 100 to 1,000 light years away. So very significant distances we're talking about. With our current technology for transportation, it would take generations to get to these worlds. The one exception is the planet we found around Proxima Centauri. 4.2 light years with conventional equipment is very, very slow, but one has never tried to create a star, an interstellar ship. Humankind is not at the point where we have actively pursued that. I think if we did actively pursue to get to the nearest solar system, we should be able to do it. And I don't think it would take generations, basically.
All right, so for those of us who aren't lucky enough to be students in your class during this amazing time of space exploration, are there resources that our audience can look into in order to engage on this kind of topic? Because this has been fascinating.
Yeah, sure. So there's a lot of great clubs out there. So this is the one scientific field where amateur astronomers can actually take a really important role. They can create real research and learn about things and have a good connection to this world through astronomy clubs. So like, I don't think that there should be any amateur geneticists out there, but amateur astronomers are super common and useful. Durham region has a great astronomical association, but if you're elsewhere in Canada, there's chapters of the Royal Astronomical Society of Canada, RASC, throughout the entire country, which I would recommend, connecting with. Also follow me on Instagram. I like to post stories. I give updates. Sometimes I'll put links for videos up there. My Instagram is Rupinterstellar. It's like my name, but interstellar, Rupinterstellar. Or on Twitter as well, just my regular name. There's so many resources out there for people that are interested in this stuff online, as well as in person when we can get there.
Are there any upcoming astronomical events that maybe people can participate in the upcoming future?
Yeah. I mean, the one that really sticks out for me is our next total solar eclipse. It's a couple of years away. There was that great total solar eclipse that happened a couple of years past. The totality didn't come into Canada. It swept the United States, but the next one that's coming to North America will actually have totality within Southern Ontario. So if you drive down to the Niagara region, for example, up to somewhere between Kingston and Ottawa, there will be periods where you will get to see the sun completely blocked by the moon, a total solar eclipse, 100%. In the Durham region, it'll be like 99.9%. Do not settle for 99.9% when it comes to total solar eclipses. Get yourself to 100%. I don't remember the exact date. I think 2023 is my guess.
Good. Great. Well, thanks so much for sharing your expertise with us today, Rupinder. This has been fantastic. As I mentioned at the beginning of our program, this is our 4th Pi Day of Giving, where we celebrate the infinite possibilities for our students here at Ontario Tech. Our students do need help more than ever, so I really do hope that participants will make a gift to our Student Relief Fund to help those students who have lost their part-time jobs or have urgent financial needs. All donations will be matched dollar for dollar. I would like to give a shout out to Kemp Travel Group for their generous sponsorship for our entire Pi Day of Giving. I hope you'll spend your lunch hour with us tomorrow as we wrap up this incredible speaker series. Again, all recordings from the previous sessions can be found on our website at ontariotechu.ca/Pi Day. Thank you again for joining us, Rupinder. Before we say goodbye, I would like to share a short message with one of our fantastic students who talks about his experiences here at Ontario Tech. So thanks so much for joining us. Take care, everybody.
On March 14th, you can help support our students. And just like Pi, the opportunities for students with a passion are infinite. So join our circle and support higher education.